Hello everyone. This is our final project for the SC205 Discrete Mathematics course, winter semester 2021-22. These are the members of our group as you can see on the web page. Our project is based on the Travelling Salesman Problem or TSP as I might address it further up in the video. In this project we have created a web page that you are currently seeing on the screen right now, and this is our entire work that we have done in the project. Then when you click over here, you can see that we have discussed about the problem in brief. We're also talking about its real life applications and a couple of its solutions. Now let's see what the problem actually is. Okay, so the TSP revolves around the cost and energy optimization. We have a salesman who is required to market his product by visiting a set of distinct cities, but the catch is that he can travel to every city only once and he needs to do the job in the most economical way possible. Also, neither can he return to his initial position until he's done marketing. Now that we have a better understanding of what the problem actually is, let's talk about the solutions. Well, there are multiple solutions existing to this problem, but in our project we have talked about only the three most popular solutions. The first approach is using the greedy algorithm. This method concentrates on choosing the most profitable alternative for the following step that is now accessible, without taking into account whether or not the chosen next step would result in the best ideal solution for the problem. Since we have mentioned the word algorithm, its algorithm is written in the slide that you can see right now. The second approach is the brute force algorithm or the knife approach. In general, it is a straightforward approach to solve any problem that involves exploring all the options before picking the best one. Here, for the traveling salesman problem, we first determine the overall distance for each potential route before choosing the shortest one. This method is not particularly efficient because it is time consuming to calculate the total distance for each and every path. The algorithm for this approach is stated as well. The third and the last approach for our project is the use of dynamic programming. It is the most effective approach to resolve the traveling salesman problem. The fundamental principle behind it is to break a problem into smaller ones using recursive division. And then, by repeatedly combining the answers to all of the smaller pieces, we arrive at the overall solution. Here, we use a bottom-up method to solve TSP. In comparison to earlier methods, the time complexity for solving the traveling salesman problem with dynamic programming is exponential, which is still better than the previous approaches. To have a better understanding, let us look at an example. Here, we have a set of 4 distinct cities which are named as A, B, C, and D. The respective distances between the cities are given in the matrix. The starting city of a journey is labeled on the row of the matrix, while the destination is labeled on the column of the matrix. So, for example, if you want to travel from city B to city C, then you can see that the distance covered would be 11 units. And if you want to travel from city D to city B, then you can see that the distance traveled would be 10 units. It should be noticed that all the diagonal elements of the matrix are 0 because no distance is covered if the salesperson remains in the same city. In other words, let's say if he travels from city A to A, then he has remained in the same city and thus no distance is covered. Let's assume that the salesperson starts from city A. Now he has the following possibilities of traveling to city B, city C, or city D. For instance, if the salesman travels to city B, then again he has two possibilities of traveling to city C or D. Again, if he travels to city C, then he has only one option of traveling to city D and then returning to city A. Similarly, all the possible routes are illustrated using this tree. To begin with the solution, I would like to approach the problem with a bottom-up approach, that is, with the help of this matrix. I will calculate the distance when the salesman travels from city D to city A, which will give me, this is 10 units. Then the distance when the salesman travels from city C to city A, which is 8 units. Similarly, the distance is traveled when the salesman travels from city D to A, B to A, C to A, and B to A are calculated using the same methods. Right. Now, let's calculate the distance covered when the salesman travels from city C to city D, which is 14 units, and add it with the previous result of travel from city D to A, which will give me the total distance covered till now. The addition will be 14 plus 10 units, which will give me 24 units. And similarly, the distance covered when the salesman travels from city D to C with the addition of the previous result of travel from C to A will give me 19 units. All such distances are calculated using the same method to calculate the total distance covered so far. Now, the distance when the salesman travels from city B to C is 11 units, and when added with the current total distance of this path, it will give us 11 plus 24 units, which will be 35 units. Similarly, the distance when the salesman travels from city B to D is 12 units, and when added with the current total distance of this path, it will give us 12 units plus 19 units, which will be 31 units. Now, between 35 and 31, 31 is the least one, so I am writing 31 over here. Similarly, the same process is done for other parts as well, and the minimum distances so far are calculated here. Now, the distance when the salesman travels from city A to B is 12 units, and when added with the minimum total distance of this path, it will give us 12 plus 31, which will be 43 units. Similarly, the distances from city A to C is 17 units, and when added with the minimum total distance of this path, it will give us 17 plus 31, which is 48 units. And the distance from city A to city D is 22 units, and when added with the minimum distance of this path, it is 29 plus 22, which will give us 51 units. Out of all these, 43 is the least one, so I'll write 43, which is our final answer. So, the shortest path that can be traveled by the salesman to do the job is A to B to D to C to A, and this distance can be covered in just 43 units. So, this is the code that we have written for the project. Here we have used the dynamic programming approach where you have used recursion calls. This is the code. It is also attached on the website, and you can see over there as well. Right now, I'm just going to run it for one test case. Now for the test case, let us consider the same example that we have used in the video. The number of cities were 4, so enter the number of nodes, which will be 4. Enter the cost of going from node 1 to node 2, which was 12. Then it was 17, then 22, then 7, then 11, then 12, then 8, then 15, then 14, alright, then 10, 10, and 11. That's the last one. So this is the same matrix that we have taken in the example, and you can see that the minimum cost is 43, just what we have calculated. So the code runs well. The traveling salesman problem is used by delivery agents to deliver the parcels to the respective customers in a way covering the shortest distance to minimize the delivery cost. It is useful in GPS maps for providing the shortest route between two places. It is used for routing long distance trains and also flights. It is used by airlines to assign flights to the crew members in a way that they return to their hometowns. Thank you.